Okay, so now it is yeah, so now it is recording, right? Yeah, yes. Just move yes. So now it's recording, and I will upload it later. So what I said is, so I can give you the mass of a particle, like the electron in this case, and I will ask you to calculate what is the equivalence energy, and this will so what you would do is the Einstein's equation is the mass times c squared is the speed of light. This is what I did here. We obtained the value in joule, and then if you want to convert it to electron volt, then you have to divide by 1.610 to the minus 19, and this will give you 511,000. Yeah, so 511,875 electron volt, or you can also divide by 1 million, and then it will give you 0.511 mega electron volt. So this is just a review of the first topic, which is this one, the equivalency, mass and energy. And let's review I will review one by one, and then I will solve the complete exam. The second one is the parameters of the wave. The parameters of the wave. So if I get, so the wave, as we mentioned in class, the wave has a wavelength, has a period t, and has a frequency. And in the case of a photon, it has also an energy. Okay. Now, and also because we will be dealing, and we have dealt only with light, it has a speed. So this is the wavelength, the period, the frequency, the energy, and the speed. Okay. So what is the relationship between the wavelength and the speed and the period? It's like the speed times distance. The distance is speed times time. The wavelength is the distance, okay? The distance traveled by the wave in one period. So it's equal to the speed of the wave times t. Now we know that the time, the period is equal to 1 over the frequency. So this means that lambda can also be c divided by the frequency. Okay, this is a relationship between the wavelength, the period, and the frequency. Okay, and then we also, according to Max Planck was the first to introduce the fact that the light is emitted or absorbed in chunks or in packets called quanta, photons. So the energy of a photon is equal to a Planck's constant times the frequency. Now the Planck's constant, we know that it's equal to 6.6 10 to the minus 34 joule second. This is Planck's constant. Now, I can also say that H, so the energy is equal to H, and I know that F, from this equation, F is equal to C over lambda. For example, if I am given the wavelength of the photon or the light, I can also calculate the energy, C over lambda. Okay. So those are the major equations between the wave parameters, and especially for light. And obviously this, if you calculate using if you calculate the energy using the value of the Planck's constant that is given here, and the speed will be meters per second, the wavelength will be meters the unit of the energy will be in joule. Then you can convert it to electron volt if you are asked to do so. Any question about this? Is this clear to everyone? And then let's go to the third topic, which is the photoelectric effect. The photoelectric effect. Photoelectric effect. Who can remind me what is the photoelectric effect? Practically, what is the photoelectric effect? Hello?
It's when the light is creating electrons from the material.
Yeah, so extracting light is extracting an electron from a metal. Yes. Yes, exactly. So light will extract, so you have, let's say, you have a metal, and under some conditions, if you have light with sufficient energy, so then you get an electron extracted or some electrons extracted. So here, what do you have? You have the energy, you have the kinetic energy of the electron, kinetic energy of the electrons. So this is the energy of light, of the light, the radiation. This is a kinetic energy of the electrons. Okay, this is the kinetic energy of the electrons. And in addition to that, the metal has a work function. Who can explain to me what is the work function? What is the work function of the metal? You might expect some questions in exam like that. Can you define what is the work function or explain?
The work function demonstrates the minimum energy that is required to extract one electron from the material.
Exactly. So the work function, yes, very good. The work function is in fact, the binding of the electron to the metal. So if you want to extract the electrons from this metal, you have to overcome this binding. So you have to provide a minimum of energy at least equal to the work function. Yeah, very good. So Einstein's equations tells us that the energy or HF, the energy of the photon, is used in two ways, in fact. The first, as you correctly mentioned, it's used to overcome the work function, and the remaining will be given as kinetic energy to the electrons. Okay. Now, please, this is most of the time. If this is okay, so here you can easily see that the light or the radiation, the incident radiation, which is light, must have at least its energy must at least be equal or bigger than the work function to extract electron, to extract electrons from the metal. Okay. So this is one remark. We talk about the threshold frequency. What is the threshold frequency? Threshold frequency is the minimum frequency that you have to provide in order to extract electrons, just extract electrons without kinetic energy. So the minimum frequency or the HF minimum is equal to phi. For example, if I give you, what is the work function of silver is, I don't know, 4.1 electron volt. What is the minimum frequency or the threshold frequency for silver? Then you have to find this quantity, which means the minimum frequency must be equal to phi divided by h. Any questions? Now, this is an important, here I want to mention something very important in this. HF is equal to phi plus k. Most of the time. Now, if you calculate HF, if you use Planck's constant and the frequency, this will be in joule. Obviously, the kinetic energy is in joule. Now, many times, what we do is we give you the work function in electron volt. For example, the work function 4.1 electron volt. Now, you have to convert to joule. Either convert everything to joule or convert everything to electron volt. This is, I'm sorry. This is one of the most common mistakes that we might do.
We're not going to have class.
Oh, I recognize the voice of one of you. Okay, so please don't either convert everything to electron volt or everything to joule. Or everything to joule. This is a common mistake.
Professor,
Yes.
I have a question. How to understand when kinetic energy should be in electron volts and when in joules when we do the photoelectric experience? Because like that's what was a mistake for me on quiz, and I still don't understand where to have electron volts and where to have joules.
Okay. So let's give an example. This is a very good question. Let's give an example. Let's assume that I have, so let's assume this is an example to answer your question. Let's say I have a light with the frequency. Frequency is 410 to the power of 15 hertz frequency. And I will assume that I have a metal that has a work function of 2.2 electron volt. Now, I am asking you to calculate the kinetic energy of the electrons, right? Now, to calculate the kinetic energy of the electrons, I know that HF is equal to the work function plus the kinetic energy, right? I need the kinetic energy, which means it's HF minus the work function, right? Are you following?
Yes.
Now, what is HF? HF is equal to 6.6 10 to the minus 34 times the frequency, 410 to the power of 15. Now, the value that you get here, let me just explain to you. I will do the calculation and then I will explain to you something that is very interesting that it can help you. 34 multiplied by 4.15. This gives you 2.6 10 to the minus 18. Now, how do you know that this is in joule and not in electron volt? Now, please just follow here. What is the unit of the Planck's constant? It's joule second, right? The unit of the Planck's constant, right? What is the unit of the frequency? Frequency is hertz, which is 1/2. You can see that you can simplify here, and it becomes joule. So the unit is in joule. Did you understand?
Yes.
Okay. So now we know that this, what you get here, is joule. But the work function here is in electron volt, is given in electron volt. Here you have two choices. Either you convert everything to joule, or you convert everything to electron volt. Now let's assume that I ask you to calculate the kinetic energy in electron volt. This is what I'm asking you. What do you have to do?
Convert the HF.
Exactly. So convert. So this means that kinetic energy, HF, must be converted in electron volt, and the work function is already given in 2.2 electron volt. So how do you convert? From here, HF is equal to 2.6 10 to the minus 10 joule, no, 10 to the minus 18. So it's 2.6 10 to the minus 18, and then you divide by 1.6 10 to the minus 19. And this will give you this will give you 2.6 by 18 divided by 1.6. This gives you 16.25 electron volt, right? Okay, so now the kinetic energy of the electrons is 16.25 minus 2.2, which is 14.05 electron. Any question?
Now it makes sense. Thank you.
Okay. Yeah. Is this clear for everyone? Those are very good questions because it's really, those are some common mistakes. Okay, so now let's go to the topic number 4, which is the de Broglie wavelength. Okay, de Broglie wavelength. Topic number 4, de Broglie wavelength. We mentioned in class that de Broglie said that, or suggested, in order to solve the problem of the fact that many things that we have seen in experimental measurement or experimental observations could not be explained by classical physics. So he suggested, okay, if light is at the same time can be described as wave, or has a behavior of wave and also has behavior of particle, why can't the particle be at the same time, not at the same time, but behave like a wave and also a particle? So this is what he said. Any particle that is moving, a particle that is moving with velocity v, that has a mass m, will have an associated wavelength, or wave, associated wave, whose wavelength is equal to the Planck's constant divided by the mass times the velocity of that particle. Okay, so this is Planck's constant. The mass in kilogram, the velocity in meters per second, and obviously the result will be in meters. The wavelength will be in meters. Okay, this is what de Broglie came up with, and this is the basics of quantum mechanics. the last topic is the Bohr model. The Bohr model, topic number 5, Bohr model for the hydrogen. Bohr model for the hydrogen. The Bohr model for the hydrogen tells us the following. If I take the hydrogen atom, hydrogen has one proton, positive proton, and then according to Bohr, there are orbits, and the electron is orbiting on those orbits. So those orbits are labeled or numbered with an integer number, n equal 1, equal 2, equal 3. So each orbit has an energy. So each orbit n, it has an energy that is equal to minus 13.6 electron volt divided by n squared. And it has a radius that is n squared times a value that is equal to 0.53 10 to the minus 10. So this is in meters and this is in electron. Okay. Now, what is very interesting here is how do we see the line spectra? So line spectra, I mentioned before that line spectra, those are experiments when you put a gas in a tube, you apply potential difference, and you start seeing light coming out of the hydrogen, for example. So those light are coming from the fact when you apply a potential difference. So the electrons get excited and they move to higher energy levels. Okay. And now those electrons, they will jump. When an electron jumps from, let's say, from level n to a lower level m, then there will be an emission of a photon of light, or photon, and the energy of this photon is just the energy of level n minus energy of level m. And we have the energies here. So all what you have to know is the number n and number m, and you plug in and you get the energy of the photon. Is this clear? Those are the three things that are important for the Bohr model, at least for our application here. So the orbit has an energy, and the orbit has a radius, and when the electron jumps from an upper level to lower level, this jump will create or will emit a photon, and the energy of this light that is emitted is just the difference between the two energy levels. Is this clear? Okay. So now I will go and start the so I will start a complete or solving a complete problem or a complete exam. I just wanted to upload the exam to OneNote. So let me just produce a PDF. Okay. Go to another. Any question while I'm doing this? Okay. So here is the exam. So this is the exam, for example, of last year. I just yeah. Okay, so you can see that in this exam, or also in the exam next week, you will receive, I mean, either I will give you the formula sheet that I uploaded, or I give you everything here. So you can see that you have everything, except the Einstein's equation, I will add it here. So here we have 4 problems, 100 point, and let's start by the first one. So the first one is lithium has a work function of 2.6 electron volt. We use a light to produce electrons with a kinetic energy of 7 electron volt. What is the frequency of this light? We have lithium, and this lithium has an energy or work function of 2.6 electron volt. We use a light to produce electrons with a kinetic energy of 7 electron volt. So, which means we use a light that will produce electrons from lithium, and those electrons will have a kinetic energy of 7 electron volt. What is the frequency of this light? Can you see my slide? The exam?
Yes.
Okay. Any idea?
We have to use formula that HF is equal work function plus kinetic energy, and from that we can find the frequency.
Yeah, exactly. So we know that the energy, or HF, is equal to the work function plus the kinetic energy. Now we have everything. We have HF, we have 2.6 electron volt, plus the kinetic energy is 7 electron volt. So the value will be 9.6 electron volt. This is the energy of light. We are asked about the kinetic, about the frequency. How can we do the frequency? Now, HF is equal to 9.6 electron volt. So this means that the frequency is 9.6 electron volt divided by H, by the Planck's constant. What do I have to do?
6.6.
Sorry?
You divide 9.6 electron volt by 6.6 times 10 to the...
So where is the mistake here? The mistake is Planck's constant. Okay, so let me explain to you here. So I have an electron volt. So from the formula point of view, I have electron volt, and you want to divide Planck's constant. The unit of Planck's constant is joule second.
Oh, so you convert it first before you divide it.
Exactly. So you need to convert this to joule so that you can see, if you simplify, it will be 1/2, which is the unit of the frequency, hertz. You see?
Yeah.
Yeah. So now, yes, you have to convert. I hope it is clear for everyone. So the frequency, first thing you have to convert. How to convert electron volt to joule?
You multiply 9.6 by 1.
Yes, 1.6 10 to the minus 19. Yeah, it is given. It will be given. Divided by the Planck's constant. Very good, yeah. And then I can so 9.6 multiplied by 1.6, 19 divided by this, and so it will give you 2.33 10 to the power of 15 hertz. This is the frequency of light. Any question? Now, the second question is, if you have any question, you can also post them on chat. What is the minimum frequency of light that can produce photoelectrons from aluminum? Sorry, from lithium. I think, yeah, this is a mistake, from lithium. Okay. I need someone else. I need someone else to tell me how can I calculate the frequency, the minimum frequency, or the threshold frequency that can produce photoelectrons from lithium. Okay, what is the threshold frequency?
We should use the work function of lithium and then using the formula converted to so the 2.6 electrovolt is the energy of a photon that we need, so we can convert it down to frequency.
Exactly, yeah. So the minimum frequency is the one that is just equal, the minimum energy that is just equal to the photoelectric, the work function, which means we are producing electrons with just zero kinetic energy. Now, the minimum will be the work function divided by h. Similarly here, this is given in electron volt and this is in joule second. So we have to convert to joule second, to joule, sorry. So again, 2.6, 1.6 10 to the minus 19 divided by 6.6 10 to the minus 34. So we do so. 2.6 divided by 6.6 34, and then it's 1.3 15. So this is no, this is so 2.6 multiplied by 1.6 19. um, 1.6 19 6. Yeah, so it will give you 6.3 10 to the power of 14 hertz. Yeah, so you can see that the minimum frequency is this one. Now, the last question, can a photon, this one, of wavelength 315 nanometers produce electrons from lithium? This is a mistake, lithium. How can you address this problem? Can a photon of wavelength 315 nanometers produce electrons from lithium? What should you do? Hello? What is the condition for the photon to produce electrons from lithium?
The work force needs to be equal to or greater than the energy,
no,
the radiation.
So equal or smaller?
Smaller, okay.
Yeah, so So the radiation must be equal or bigger than the work function. So this is what we want. This is what we want to check, right? Hello, can you follow? Hello?
Hello.
Yes.
Yeah. So this is what we want to verify. So this means I have to calculate. What do I have to calculate? I have to calculate the energy of this light. Do you agree? Are you following?
Yes.
So how do I calculate the energy of this light? I'm given the wavelength. How do I do? If I give you the wavelength of light, how can you calculate the energy of the light? Hello?
Using the formula converted to energy, I think I can't remember the formula, the exact formula.
So we know that the frequency is equal to the speed of light divided by the wavelength, right? So H C over lambda. So the energy of our light is 6.6 10 minus 34 times the speed of light divided by the wavelength, which is 350 nanometers. I have to convert to -9. Are you following? If you don't understand, you can
Yes.
write it on the
Yes.
chat. 6.6, 34 multiplied by 3 to the power of 8, and then divided by 350 power of 9. So this will give me 5.7 10 to the minus 19. What is the unit here of the energy?
Electron volts.
It is joule. Why it is joule? Let me explain to you why it is joule. I'm calculating this quantity. This quantity, Hc over lambda, if I look at unit, what is the unit of Planck's constant? Joule times second. What is the unit of the speed of light? Is meters per second. And what is the unit of meters? Of a lambda is meters. So second I can cancel, and meters I cancel, and I get joule at the end. Are you following?
Yes.
Yes.
So this is joule. This quantity is joule. But the work function is given in 2.6. So in order to test this, I have to convert the energy of the photon to electron volt. So which means I have to divide by 1.6 10 to the minus 19. So the HF will be equal to 3.56 electron volt, which is bigger than 2. What is the value? 2.6, yeah, which is bigger than put. Are you following, please? Did you understand what I did? Hello?
Yes.
Yes.
Okay. So what I did, I wanted to check this one. Let me write it in blue. I wanted to check this one. I wanted to check if this light is sufficient to produce electrons from lithium. In order to do so, I have to check if the energy of this light is bigger or equal, at least equal, to the work function. So the first thing I have to calculate the energy of this light. The energy of this light is HF, but since we are given the wavelength, it is equal hc over lambda. I replace by h, by c, and by lambda. Whenever you do this calculation, the unit is in joule. But the work function is given in electron volt. So in order to compare both of them, so then I have to convert this to electron volt, which means I divide by 1.6 10 to the minus 19. So this is what I get. So this is the energy of light, of this light in electron volt. And you can see that it is bigger than the energy, the work function, which means yes, it can. Any question? Okay, so now.
So I have a question.
Yes.
So in the exam, can we just say like yes or no?
No, but you have.
Without.
No, you have to tell me. Well, I need to understand to know that you understood how to get it. How would you know yes or no?
Like
But,
maybe you just calculate it somewhere else, but you don't show it.
no, you tell me. At least write this one. At least write, okay, the energy of the light is 3.56 electron volt, which is bigger than 2.6 electron volt. Yes. Okay. Okay, an electron is accelerated at a speed of 410 to the power of 5 meters per second. What is the momentum? Do you remember the momentum? Momentum is the mass times the velocity. In fact, here the question is about the Broglie wavelength. What is the Broglie wavelength? Lambda is equal to h over mv, or also h over the momentum. That's why I asked the momentum. So the momentum here, I know that the electron's mass is 9.1 1031 times the velocity that I'm giving 10 to the power of 5. Okay, here I can calculate it. 9.1 31. So this is 3.64 10 to the minus 25 kilogram meters per second. This is the unit of momentum. And what is the Broglie wavelength? The Broglie wavelength is h over this one. So it's h over mv. It is 6.6 10 to the minus 34 divided by the value that we found here, which is 3.6 10 to the minus 25, and the value would be in meters. So it will be 1.8 10 to the minus 9 meters. This is the wavelength. Any question? This is an easy question. Is this clear for everyone?
Yeah.
Okay. Okay, so this is not included in the exam. It will be in the later in the quizzes because we did not finish the shells. So this is the one that will be interesting. So in the Bose model, the electron is orbiting around the nucleus in circular orbit. What are the energy and radius of the fifth level? How can we do this? So I'm asked to calculate the energy of the fifth level. Any idea?
Do we subtract the N5 minus N? No, okay.
No.
E is equal to,
Yeah. Here, I'm just asking about the fifth level. So which means in general, it is minus 13.6 divided by n squared. This is an electron volt, and the radius is n squared times 0.53 10 to the minus 10 meters. So this is all what you have to do. So E5 means it is minus 13.6 divided by 25, right?
okay.
So here, so it's divided by 25. This gives you minus 544 electron volt. Same thing for radius 5, it will be 25 times 0.53 10 to the minus 10. So this will give 25 0.53. It will give you 13.25 10 to the minus 10 meters. This is the answer. I'm asking about just one level. Now, the question here, the electron undergoes a transition from the fifth level to the third level. What are the energy and the wavelength of the photon emitted? Okay. Now we can, now we apply what you just said, right? So I have an electron that is in the fifth level, and it goes to the third level. So the electron goes from here to here. So there will be a photon emitted, and the photon that is emitted, its energy, which is also HF, is equal to the fifth minus the third. Are you following? Okay. So now let's calculate. Please pay attention to here. So the photon's energy is equal to E5 minus E3. What is E5? E5 is minus 13.6 divided by 25. Are you following? Minus. Hello?
Yeah, we follow.
Okay. Minus E3. E3 is minus 13.6 divided by 9. So minus minus is plus. So this means that minus 13.625 plus 13.6 divided by 9. So most, you can, so we will do the calculation. So it is 0.97 electron volt. This is the energy of the light. So the light's energy is 0.97 electron volt. Okay, so now my question, how can I calculate the wavelength of this light? This is the energy of the light, right? I know that the energy is equal to HF, but also is equal to HC over lambda. Are you following? Because the frequency is equal C over lambda. C. Hello, can you think there was an interruption? Can you hear me?
So I think you are breaking.
Okay. Let me just see if I can solve the issue here. Now, can you hear me? Can you hear me now? Hello? Can you hear me?
Yeah.
Okay. So what I was mentioning that I got the energy of the photon that is equal 0.97 electron volt. I want to calculate the wavelength. Did you understand this?
Which one?
So the energy of the photon is equal to HF is equal HT over lambda, right? Because the frequency is T over lambda, right? Hello? Is this?
Yeah.
So now I want to calculate the lambda. So lambda will be equal to HC divided by the energy that I just found, right?
Okay.
But this value will be in joule and this value in electron volts. So I have to convert this value in joule also. Please do not forget this one. So the value, so I have to convert. So this will be 6.610 to the minus 34 times the speed of light, 3/10 of power of 8, divided by 0.97, but now I have to convert it to joule. Is this clear to everyone? Hello?
With the wavelength, we do not subtract anything
Why do you have
because
to?
it's saying that there's a transition from the fifth to the third level. So after we subtract for the energy, we just
We
use
got,
that value.
yeah, yes, we got, this is the photon energy. This is the energy of the photons that is emitted. We already did the subtraction here.
Oh.
Now I obtained the photon of energy. But this, the energy of the photon that I obtained is given in electron volt. I want to calculate its wavelength. Before going to the wavelength, the first thing I have to do is to convert the electron volt to joule. And then I use this formula. Did you understand? I did not hear you.
Yes, I understood.
No, you want me to repeat?
I just wanted to clarify, is the SI unit for the wavelength joules?
Sorry, I did not understand.
I wanted to clarify if the unit for wavelength is joules.
No, it's meters.
So why are we converting?
Okay, yes, let me explain it right now. Okay. So HF is given in joule, right? So let's say this is 0.96 electron volt, right? Or 97. Yeah, 97. This is the energy of light, right? And I want to calculate the wavelength. The wavelength is hc over lambda, right? Because the frequency is c over lambda. Now, in order to isolate the wavelength will be equal to hc over 0.96 electron volt. Are you following?
Yes.
Now, let me tell you here. So I will stop here and talk about the unit of this quantity. What is the unit of this quantity? I know that joule, the unit of Planck's constant is joule second. And the unit of the speed of light is meters per second, divided by the unit of an energy. This one, energy. So if I do this, right?
Yeah.
This is in joule. This must be in joule because then I can cancel and I get the unit of the wavelength, which is meters.
Yes.
So that's why you have to convert this to joule because this one is in joule.
Oh, okay. Okay.
Okay.
Yeah.
Yeah, so I am done with this review because I reviewed all the topics. If you have questions, please ask.
Do we get practice questions?
Yeah, actually, I already uploaded one full exam. I sent you an email yesterday.
Oh, okay.
Yeah. Any question? If not, I will just stop here and I will upload this video and send you the link. Okay.
All right. Thank you.
Thank you very much. Thank you. Sorry for today. I just didn't want to infect everyone. Okay. Thank you.
That's okay. Feel better soon.
Thank you. Have a nice day. Bye-bye.